Okay, so I think this should end up being the last chunk of video here for the slideshow on chapter 12. I feel like I'm doing a good job of highlighting why I don't like to use PowerPoint. You can talk an awful lot and go through a lot of slides and actually show very little. But last time I was trying to show some ionic unit cells and how we can think of the anion lattice and the cations fitting in to different places in that lattice. Well, the different spaces in the lattice actually have different sizes. So how big the cation and the anion are is an important factor in identifying what type of structure is possible. And some of that is shown on this slide. So the size of the cation compared to the anion, so we're going to ratio the radii of those two pieces, is the major factor in figuring out which structure you're going to see. Now, there's some really nice pictures here that show the cube, the octahedral, and the tetrahedral shapes. So this particular over here on the right, this figure of zinc sulfide, I think is really nice to show the tetrahedron I was trying to point out on the last slide. So you can kind of get an idea of the cubic hole for cesium chloride versus, use the pen, for cesium chloride versus the octahedral hole for sodium chloride versus the tetrahedral hole for zinc sulfide. And you can see in the picture here, the arrow, decreasing radius of cation to anion. So as the cations get smaller, they're more likely to end up in tetrahedral holes. As the cations get larger, kind of approaching the size of the anion, like cesium here, they're more likely to end up in a cubic hole. And there's some information about the radii here in the slides, where we can actually calculate that ratio. And this is pretty well described, I think, in the textbook and in some of the practice problems. You can just calculate the ratio of the radii of the cation and the anion. And that gives you a pretty good idea based on what that number comes out to be, where that cation is likely to fit if we think about a lattice composed of the anions. And you'll see a couple problems like that in your textbook. Okay, the last couple slides here, which I think I can get through before this video gets too long, are materials that are not metals or that are not made up of atomic solids or ionic solids, but are solids made from molecular materials. And there's a couple things I want to point out here. A molecular solid, these are atoms or molecules held together by weaker forces, so dispersion forces or dipole-dipole forces or hydrogen bonds. And the shape of the molecules is going to be important in terms of how the molecules stack together. So there's a couple things I want to kind of describe here, over here on the side. The first kind of table up here at the top shows a series of compounds. Now, they're using an abbreviation here where every bend in the structure here is a carbon atom. So this is 6 carbon atoms connected in sort of a ring structure for benzene. And we're given the melting points and the boiling points here. And if we start with the boiling point, because we're familiar a little bit with intermolecular interactions, 80 for benzene goes up to 111 in toluene when you add this extra carbon on the end, and then it jumps up to 182 for phenol where you have a OH group on the end there. And we should readily understand that, I think, from intermolecular forces we talked about in chapter 10. Benzene is a hydrocarbon, just carbon and hydrogen, so it's got London dispersive forces. It's got a reasonably low boiling point. It's a liquid at room temperature. Toluene, still a hydrocarbon, but we added this extra chunk of surface area up here with this other carbon connected to 3 hydrogens. A little stronger London dispersive forces here, and that cranks up the boiling point a little bit. Phenol, we now have the possibility of hydrogen bonding between the molecules, so the boiling point jumps up quite a bit. Now, what we need to think about with solids, if we want to think about how physical properties relate to structure in solids, we want to think about melting point. Well, melting is solid going to liquid. That's a little different than what happens in the boiling point where the liquid becomes a gas, because solid and liquid, the molecules are still close together. So we see a different trend here. The melting point for benzene is 5, but the melting point for toluene is significantly lower. It's minus 95 degrees Celsius here. Now, phenol does move up a little bit, so the trend from benzene to phenol is about the same as we saw up here. There's a jump, right, that corresponds to the strength of that hydrogen bonding interaction. But what makes toluene so much lower than benzene? It's a function of structure, but we have to think about structure a little bit differently. Solids are based on the ability of the atoms to link together in an ordered arrangement. You can think about benzene here almost as kind of shaped like a plate. It's really easy to stack up plates, right, in the cabinet. So you can stack the benzene molecules up pretty easily and make a fairly ordered arrangement, so it's not so hard to kind of freeze benzene into a solid. Toluene, though, isn't a plate anymore because it's got this handle sticking out. So if you try to stack up toluene molecules, that's more like trying to stack the pots in your cupboard. It's really hard to stack the pots because the handle is sticking out that prevents one from kind of sliding into another. So it becomes much harder to make toluene into a solid. So you have to go to a significantly lower temperature before you can find that ordered arrangement. Okay, the other physical property I want to talk about here is graphite. So graphite is basically a two-dimensional material where you have lots and lots of layers of sheets of carbon atoms. And one of the uses of graphite you may be familiar with is it's a lubricant. Now, also it's in a pencil. So you put it in the pencil, you can run the pencil across the paper, and little bits of graphite are left behind. And that corresponds to the strength of the interactions here. There's a really strong set of interactions between the carbon atoms in each sheet, but then there's a really weak interaction between the sheets. So when you run the piece of graphite across the paper, you can break these weak interactions between the sheets. And this is also why graphite's a good lubricant in like a Pinewood Derby car, if anybody's been in Cub Scouts, because as the sheets move past each other, you can kind of lubricate the axles in your Pinewood Derby car. So that's a function of, excuse me, the three-dimensional structure of the molecules. Now, with carbon in particular, we talk about graphite because we also want to talk about diamond. A diamond is a particular kind of solid called a covalent network solid, where every atom is covalently bonded to another set of atoms, and extending those sets of bonding interactions out into three dimensions is what gives you the overall structure. So in diamond, every carbon is tetrahedral, right? In the previous example, graphite, they were trigonal planar. Every carbon here is tetrahedral, so each carbon is connected to 4 other carbon atoms. Each of those is connected to 4 other carbon atoms, extending out into three-dimensional space. Now, this is what gives diamond its kind of famous strength. Anytime you would try to, say, scratch a diamond, you would have to move a carbon atom that's kind of embedded into this structure. So very strong material, right? And these will tend to have higher boiling points, higher melting points as well. So that's the end